So in section 2, we're going to look at the graphs of some exponential functions and kind of see some properties they have, talk about how you can transform them using some basic functional transformations from algebra. So exponential functions in general have the form of f of x equals a times b to the x. And the big thing is a is any number, but b has to be greater than 0. And x can be any number. But generally, b has to be bigger than 0 because if you have a negative base, then negatives multiplied by themselves will switch signs. We also generally don't want to use b equal to 1. That's typically something we don't want to look at. Because if you take 1 to any power, it's always 1. So it's just kind of a very, very constant function. Now the domain of a typical exponential is negative infinity to infinity. So I can plug any x value into a function. So if I have, for example, let's just do an easy one. Let's just say I have 4 to the x. I can plug any x value in. The range is what is actually a little different. The range is actually 0 to infinity. I can never plug in a number for x in an exponential and get 0 or a negative number. And the reason is, if I plug in 0 to this function, anything to the 0 is always 1. Anything to a negative number, let's say we do 4 to the negative 2. Remember, negative exponents means you write it as the reciprocal. So 4 to the negative 2 is 1 over 4 to the second. So these are kind of important exponent rules where we kind of want to remember how we plug in, how we evaluate the function. So there are going to be two types of exponential functions. We're going to have ones that grow and ones that decay. Okay. This first type function, this blue function here, is an exponential growth function. And it's growth simply because the y values are increasing as the x values increase. So it's going up. Now, why do we have an exponential function that grows versus what we'll call decay? It's what the base number is. And for something to grow, we need the base to be greater than 1. So any times that base power that you're raising x to is bigger than 1, we'll have exponential growth. Now for the red one here, this is exponential decay. It's decay because it's going down. It's kind of the y values are decreasing as the x values increases. And we get decaying if the b is between 0 and 1. So if you have a value between 0 and 1, your function is going to decay. So our big goal in this section is to look at some functions and to graph them, to talk about some of their parts, to talk about their domains, their ranges, their intercepts. And another thing you see both of these, hopefully you notice both of these have a horizontal asymptote. Both of them at 0. If I think of this horizontal line here, both of these exponential functions will approach that line but not touch it. And again, that's shown by the fact the range is 0 to infinity, so it's never going to touch 0, never going to go below 0. All right, so let's graph some exponential functions, just kind of see what they look like. Now I'm going to start by just plotting some points, like we traditionally do in functions. And then we can kind of see some of the parts, what's going on with it. So I'm going to pick some x values. I'm just going to pick some values 2, 1, 0, and negative 1. So we have some positives, we have some negatives, we have 0. So I'm essentially just going to plug this in. So 2 to the second is 4. 2 to the first is 2. 2 to the 0 is 1. Remember we said anything to the 0 is 1. And 2 to the minus 1 is 1/2. And the reason it's 1/2 is 1 over 2 to the first, which is 1/2. So these are some ordered pairs I can plot, and hopefully the graph looks similar to what we had above. Now remember, since this was a base, the base in this case was 2. This was a growth function, so we should see a graph that's going up. So let's go ahead and plot these points. So we have 2, 4, which would be here. We have 1, 2, which would be here. We have 0, 1, which would be here. And we have negative 1, 1/2. So you can see from these points, when I connect them, it looks just like this. Now, this does not have any x-intercept, so there is no x-intercept. There is a y-intercept. The y-intercept is at 0, 1. When we look at the inverse function of logarithmic functions, you'll see how these will sometimes change. We could also talk about the asymptote. There is a horizontal asymptote at y equals 0. Let's go ahead and look at the next one. Pretty similar, it's just 4 to the x. This base is also greater than 1, so we would assume that it would also grow. So if I put the same values in, I get 4 to the second, which is 16, so a lot bigger. 4 to the first is 4. 4 to the 0 is 1. 4 to the minus 1 is 1/4. So if I plot these, obviously we can kind of see some differences. 1/4, so that point is going to be way up here. 216 is way up here, it's off the graph. We have 0, 1, and then we have negative 1/4 this time. So if I graph it, it looks very similar, but what you can see is it's actually growing at a faster rate. If you compare it to the one next to it, it grows a lot faster, especially once it gets past the value of 0. Also has some very interesting parts. Again, no x-intercept. This has kind of been a theme. You'll see a theme in all these. The y-intercept, again, is going to be 0, 1. And the horizontal asymptote is going to be at y equals 0. Now, these will eventually change, but for these first couple, nothing crazy. So this last one, we now have an a value. The a value is 1. So when I'm doing my values, and I'll just do the same old ones, so I'm doing 3 times 2 to the second. So remember order of operations, we would do the exponent first, and then we would multiply by 3. So 2 squared is 4. 4 times 3 is 12. Same thing for 1. We have 3 times 2 to the first. 2 to the first is 2 times 3 is 6. 3 times 2 to the 0 is 3 times 1, which is 3. Then we have 3 times 2 to the minus 1, which is basically 3 divided by 2, so like 1.5. So you'll notice for all these points when I graph them, so I have 212, which is just slightly off the graph, not too bad. We have 1, 6. We have 0, 3. And we have negative 1, 1.5. So the curve looks like this. It actually still will have a horizontal asymptote of 0, just gets there a little slower. So if we think about this one, still, again, no x-intercept. But the y-intercept here was 0, 3. And if you notice, the a value in our thing was 3, the value in front of the exponential. That is what's going to affect the y-intercept. Horizontal asymptote, again, at y equals 0. Now, for all these, you, of course, could just graph on Desmo. You can see some points. You can see these features. But it's good to kind of graph them by hand, kind of see why you get the values you get. So now we're going to look at the graph of some other exponential functions, ones that have been moved and transformed by some different movements in the equation. So we look at this equation, kind of reviewing from algebra. If you move a value in the function, in the input of the function, then it's going to move it left and right. So in an exponential, that's done up here in the exponent. So h is going to be the horizontal movement. So if h is positive, it's going to move right. And if h is negative, it's going to move left. But you have to be careful because notice h comes after the negative sign. So if I have a function y equals 2 to the x minus 1, that actually moves right because the 1 is the thing that happens after the negative sign. So you have to always remember it's always the opposite of the sign you see there because it's what happens after a negative sign. The value a, which we saw before, is going to change the intercept, but it also does lots of things. If a is negative, it's going to flip the graph over the x-axis. So instead of going up, it's going to go down. If a is bigger than 1, it's going to stretch the graph. So it's going to increase that y-intercept. And if a is between 0 and 1, so a fraction, 1/2, 1/3, something else, we say it compresses. So it's going to press the graph down. The last one, and probably the most important one, is k. And k is the vertical movement. So k is going to shift it up and down. And if k is positive, it moves up. And if k is a negative, it moves down. This is important because this is really going to influence what our horizontal asymptote is. So if I look at the couple examples I have here, this first one says, given the graph parent function 2 to the x, so this function I have here is already 2 to the x, I want to graph these new functions. So this one you can see is x to the minus 2 in the exponent, so this is going to move everything right by 2 units, because the number that comes after the negative sign is 2. So that's the transformation. So if I move all these points I have on here to the right by 2, it'll look something like this. So the graph will just kind of go up like this. Now, of course, I would encourage you to graph both the original 2 to the x and 2 to the x minus 2 on Desmos, and you can see how it does this right movement. Now, the asymptote doesn't change. It's still y equals 0, because it just moves it to the right. Where it approaches is still going to be the same. Now, since exponentials and logs are inverses, we like to talk about those a lot, so we can actually also find the inverse function of this. So if you remember how we find inverse functions, this function is y equals 2 to the x minus 2. So to find the inverse function, we simply switch x and y. So this becomes x to the 2y minus 2. Now the trick here is we have to resolve for x, or for y, pardon me. So we'll have to move it around, and then we'll have to use our log form. Remember, the inverse of an exponential should always be a logarithm and vice versa. So if I add 2, I get x plus 2 equals 2 to the y. And then if I want to change it to inverse, or to logarithmic form, I get y, which is the exponent, equals log base 2 of the x plus 2. And again, just recall, whatever was the exponent exponential goes by itself, the base goes here, and whatever was on side of the equal sign goes here. So it's just a rearrangement into this log function. So this log function is the inverse function of 2 to the x minus 2. Let's look at another example. Here we have 2 to the x minus 2. But now you see the minus 2 is not in the exponent. It's outside the function. So this one is going to go down by 2, because the number on the outside is our k from above. So that's going to move it down 2. So if I move everything down 2, it's going to look something like this. Just moving all the y values down 2. Connect my curve, something like that. But now the big thing is, it has moved the asymptote down. The asymptote used to be at 0, but by shifting it down by 2, the horizontal asymptote is now y equal negative 2. And that k is really what drives what your asymptote is. We can look at the inverse function of this one as well. So we have y equal 2 to the x minus 2. So I will do the same thing. X equal 2 to the y minus 2. I'll add it. X plus 2 equal 2 to the y. And then I can change it to log form. Log base 2 of x plus 2. Okay, the next one you see negative 1 to the x. So this means our a is negative 1. So remember, when a is negative, this is going to flip over the x-axis. So all the values are going to get flipped to the other side. So this y value flips, this point flips, this point flips, this point flips. That's at 4, so it'll be right here. So you can see it kind of goes like this. So the asymptote actually doesn't change. The range would obviously change, because now it's negative infinity to 0, but it just flips. So, inverse function, y equals -1, 2 to the x. So if I flip it, I get x equals -1, 2 to the y. So I'll just move the -1, I'll just multiply it to both sides to get -x, 2 to the y. And then if I change the log form, we get y log base 2 of -x, just doing that rearrangement. Very important to get that rearrangement down for the log functions. Let's look at a couple others. So this one we have 2 to the x plus 2. So remember what I said, this is actually going to go left by 2. Because remember we said it's always what comes after the negative sign, so if it's x plus 2 in the exponent, it's the opposite. So all these points are going to move left by 2 units. And so our function is going to look something like this. Now again, that does not change the asymptote. Hopefully you're kind of seeing that the only thing that will change the asymptote is that k value. So this is y equals 2 to the x plus 2. So to find the inverse, I'll switch the x and y. So I'll go ahead and change this to log form because I have it as the exponent. So I have y plus 2 equals log base 2 to the x. And then I'll simply subtract 2. So y equal log base 2 of x minus 2. So that minus 2 is outside the log. Same thing for the next one. The next one is 2 to the x plus 3. This is going to shift the graph up 3 because, again, it's on the outside versus in the exponent versus outside. So shifting everything up 3. This one will be up here. This one will be here, 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 and here. So the exponential looks something like that. And again, we are, with the up and down, we are changing the asymptote. So the asymptote in this case is y equals 3. Now if I want to find the inverse function, remember y equals 2 to the x plus 3. I'll switch x and y just like we always have for inverses. So x equals 2 to the y plus 3. And I'll just solve. So I'll subtract 3 equals 2 to the y. And again, I subtract 3 here, and I didn't on the last one first because it was in the exponent. So this will be log base 2 of x minus 3 equals y. Finally, the last one with this base 2. Now in this case, you'll notice we have not only the negative, so it's going to flip over the x-axis, but it's also a 2, so it's also going to stretch the graph. Now the easiest way to do this is, since it's a -2, we're just going to multiply all the y values by -2. So if I take this point here, which is at 2, I'll flip it, which would be at -2, but I'm also doubling it, which would make it at -4. Same thing for 1. 1 would flip to -1, but I'm doubling it, so it would go to 2. Same thing for this one. This one's 8, so it would be at -16, so it's way down there. Same thing for this one. This one looks like it's at a half. Double a half flip to be here. So it just grows a lot faster. It's just a lot more steep of an exponential in this case. Asymptote doesn't change because the k value, there was no k value, no up and down shift. Inverse function, same thing. Y equals -2 times 2 to the x. So I'll switch x and y. And these inverse functions are really not as important for exponentials. They become really important when we do logarithms in the next section. So I'll divide by -2 to get that variable by itself. So I get x over -2, 2 to the y. And then I can simply change the log form. So log base 2, again, the exponent goes by itself of x over -2. So hopefully this is a pretty good idea of how an exponential graph looks, how it moves, how it shifts. The key thing to remember is you can always graph these on Desmos and see how they look, how they work, what they actually look like.